Okay, so these are some discrete distributions from which you should know these two by heart, and this one maybe it's not that important. So the binomial, you can use it if you have like a maximum number, and then you want to know how much from that number is the occurrence. So that's K, the occurrence of an event, and it's the total number, and P is the probability. So this can be used, for example, for 40 coin flips, and then see how much head comes up and how much tail, stuff like that, or yeah, everything that you have a maximum. If you don't have a maximum, you can use a Poisson distribution that has a rate that you can use for example, car crashes, because you don't know maximum car crashes, but you know how much on average will happen. And then you can use that as this, as the lambda, and then K is the number of occurrences that you will sample. And the Bernoulli is a special case of the binomial where you have one coin flip only, or one n, and then it will come to this, because if you put an n here, one here, it will be 1 minus k. And if you have a 1 at the top of this, it will be 1. So it leads to this. You can use it for one coin flip, or like this set parameters we saw earlier when you had multiple models. And these are the expectations. They are not really important to know, but maybe you can write them down if you want to. Is everybody done with writing, or can I continue? Okay. Oh, yeah. Boom. Okay. So these are some continuous distributions. You've seen the beta, yeah, you've seen all of them. Beta is used as prior for Bernoulli and binomial distributions. You have a shape parameter and a rate parameter. Yeah, then variable x, what's most often it's x is theta. And then you can also, we saw that there's one exercise, I think you can write A and B as this. And then you can also do the other way around, and then you have more like mean and standard deviation around the mean, which can be helpful if you want to interpret the beta distribution. It's between 0 and 1, so it's useful for like beta and Bernoulli. Then we have the gamma distribution. It's pretty similar, but a little bit different. But the difference is that here the outcome can be above 1, so you can use it for a standard deviation, for a Gaussian distribution, or for a Poisson or exponential. And you again have a shape and a rate parameter, very similar. And then you have the normal. I think you all know that one. So you have a mean and standard deviation, and it can be negative, can be larger than 1, can be everything. Yeah, first you, then get but first you.
How do I just stop sharing? There you go.
What is this? This is a Minecraft. Yes. It's not my Minecraft. I only play FIFA 14. Chicken head. Oh, dragon head. Yeah, that's one. Yeah, I think that's more precious than the dragon head. Yeah.
Where is it? Oh my god.
Should I drink some blues?
No. Is this it? Is this the one you were at?
Yes.
Okay. I will check it
Yes.
louder.
Gamma can be larger than 1, and beta between 0 and 1. So therefore, yeah, that's a bit. I was also confused when I read it again, my slides, but That's for this. What? Yeah. Yeah. Yeah, but maybe I don't think. No, this should be not be there. It should be larger than 0. I think. I was also, but you can use it for prior for Poisson and exponential, and that can have numbers larger than 1. So I think it should be larger than 1. Yeah, so that's used for coin flips or stuff like that. Yes. I didn't make this slide last year, so maybe there are some mistakes in there. I will put them here. Or I did make it, but I just say I didn't make it. Yes, this is the beta. And this is gamma. Yeah. Hello, online. So this is the gamma distribution, and this is the beta distribution. So as you can see, like, oh, maybe I should use the mouse. This is a normalizing constant. So that's why the beta distribution falls between 0 and 1. This one doesn't have a normalizing constant. Okay, this is the normalizing constant, and this one doesn't have a normalizing constant. It does have some division, but it's not a normalizing constant. Okay, was that clear for online? Oh, there are some chats. Yeah, we don't even see the slides, but that was 5 minutes ago, so you fixed it, right? Now we do. Great. So the top one is gamma and the middle is beta, indeed. And the lower one is the normal, that's correct. Yes. No, I think that's only for the beta. Yeah, but there's a different. You can also write it different, not in this way, but with also with a shape and a scale. So this is shape and rate. But for the gamma, you can also write it as 1 over beta, and that's a scale. And then, yeah, it becomes a little bit different. But so it's theta is 1 over beta. Beta, yeah, not the distribution, but the variable. Okay, is everybody done? And is there no more confusion? Okay, let's continue. Yes, so conjugate. So I already mentioned some which distributions belong to other ones, but the problem is when we do Bayesian inference, the marginal likelihood, you have an integral and it can be infinite or intractable. So we can't find the posterior distribution. So a solution is to use conjugate distributions. So the posterior has the same form as the prior. So if you use beta as prior for Bernoulli, posterior will also be a beta, but with different parameters. Same for everyone on this list. And the conjugate prior of a normal distribution is just a normal distribution. And to find the posterior, you can use the proportionality. So because the marginal likelihood is one number. So if you divide it, it doesn't change. If you leave it out, it doesn't change the shape of the distribution, but only the scale. So you can to find the posterior parameters, you can also just multiply the prior with the likelihood. And we will see an example of that later. Yes, can I continue? Okay, so MCMC, yeah, Monte Carlo, something. The basic idea is that you approximate the posterior by creating random walks through the distribution according to some criterion. So we know the likelihood and the prior. Prior is often flat, so we only look at the likelihood, and then we propose samples and see if they are better or worse in their likelihood. And if their posterior has more likely areas, the random walk will visit those areas more often. So how do you do MCMC? You start at a random location, and then you make a move to proposed location with this. So with to a higher number or lower number, and then we accept that move using this formula. So we divide the proposed location by the current location, and then if it's larger than 1, we use 1 as probability. So we always go to the new location. If it's lower than 1, so the current is better than the proposed, then that's the probability. And so there's still a chance that you go to the worst location, but sometimes you also stay in your location. Yeah, that's it. Is MCMC clear? Because I think you also work with it a lot, so you know how it works, and you don't have to apply it. You only have to know stuff about it. I hope for you. So how do you check convergence? So you can use MCMC because if you don't run it for enough iterations, the random walks are not similar, and then we can make a good conclusion. So you can use trace plots and plots and just look at similar, and that means we can make a good parameter should be. For this one, you can see if burn-in is necessary. So for this one, we can see at the start they are really different, but if we look here, they all become more similar. So we can burn in the first samples. And autocorrelation, I don't know if it was in the lectures this year, but it means if there is some other variable that influences multiple variables, then the samples are not real because they're based on each other. Yes. Oh yeah, so that's because they're really different. So we only take the samples from 100 forward. So that's a burn in. You burn the first few samples. Yes.
So if they have not converged,
yeah. And that's why it's also important to have multiple chains, because you can see if it has converged. If you only have one chain, you don't know if it has converged. I think that's just my voice, that the sound is weird. What's wrong with the sound? Or do you know what's happening? Because it's in the chat. Oh, it's fine now. Sometimes it cuts out. Okay, whatever. Where's okay? So the most important part of Bayesian statistics is model comparison. We want to so you can use this to get the parameters based on a given model. So we can use Bayes rule, but we can also compare two models and see which one is better or more likely given the data. So we have prior odds, Bayes factor, and posterior odds. And then if the Bayes factor is higher than 1, model 1 is better, and if it's lower than 1, model 2 is better. But then depending on how big or how small it is, it's better evidence. And yeah, so this only used for one model and to get parameters given that model, and this is to compare two models. Yes, so more model comparison. Yeah, if you, this was on the last slide, but this, I think this is an example. So if we have these two given set and n, so it's a binomial distribution, we can, that we don't know the posterior distribution, so we can calculate in this way. Most of the time we don't have any prior odds, so both are 0.5, and then if you divide them, it's 1, so we only have to calculate this part. You saw that many times before. And then here are the two steps. So the two models are these examples from the slide. Two models are this, and then this is the data, and we can calculate them using the binomial stuff. And then we get these two outputs, and then we can divide them because we have this. So this is the base factor. So we see model 2 is better than model 1. Prior odds are this. I already mentioned that. So the posterior this, and then using this magic, we can calculate the posterior odds, the posterior probability for both models. So we know that the sum of both models is 1. So we can say probability of model 2 is the same as 1 minus probability of model 1. And then if we fill that in here, we get this. So this divided by 1 minus model 1 is that number, and then you can rearrange that to this. And then you can calculate that, and then if we fill it in here, we also get the posterior probability of model 2. Is that clear? Yes. Okay, the Savage-Dickey density ratio. You also worked with it, so I hope you still know what it is. We have not two different models, but we have two different hypotheses. So one is a zero hypothesis, where, for example, difference is 0, or weight, and we want to see if it's important or not. And then we can test these two. So H1 is there is a difference, or the weight has a value that's different from 0. And then we can compute it this way. So model 1 is hypothesis 1, model 2 is hypothesis 0. And yes, no, the other way around. So this is for, okay, yeah, no, it's the same. But this is for the prior, this is posterior. So here we didn't see the data yet, and here we did see the data. So if the probability is higher than 1, it means that there's more probability or more evidence for that the difference. Yeah, here it's 0.5, but let's say H0. So there's more evidence for no difference, or value of weight at 0. In the prior, so before we saw the data than after we saw the data. So that means that probably H1 is true. But if this number is smaller than 1, it means that there's more evidence in the posterior for hypothesis 0. So it means that hypothesis 0 is probably true, because given data, it's more likely that there's no difference. Is that clear? Okay. Some important Bayesian concepts, so shrinkage. I think you saw that one in practice in the practice exam, the first question, that you have 3 different settings and then with 5 data points. And if we would combine them as one setting of 15, then we would it would be influenced by the prior by the outliers a lot, and we would get a mean that's off. If we use a generated model like this with shrinkage, then we can say 2 are around this mean, 1 is an outlier class. But it doesn't influence theta or the omega as much. Is that clear what shrinkage does? So you can have different parameters for every setting or every model. Yes. Yeah. Yeah, and it decreases the difference between variables. It puts them together because you have a prior. Okay, then we have Occam's razor. That's like more just a statement. Among competing models, the one with the fewest assumptions should be selected. So if we have this one is more specific, but less complex. This one was more complex one. I read about it. Forgot again. Okay, so if we have two models, one is very complex, one is not complex, and for example, if the data is the very simple model doesn't perform well, then we choose the very complex one. But if they both perform well, so around this part, can only explain a little bit of the data, while this one can explain a lot of the data, but around this part, we choose this model. Is that clear?
Sorry, I still struggle to understand what shrinkage was.
Yeah, so in the example exam, we had 3 data sets or 3 settings, and 2 had like a mean of 9.8, and another one had a mean of 6 or something. And if we would put them in one, like we just calculate the average, then it's very much influenced by the outliers. But if we would put a prior on it, and like this, each setting samples something from that prior, then that prior is less influenced by the outliers, because it pulls everything together, so it's less influenced by outliers, and yeah, it can estimate the mean better. I think if you do did you already look at the practice exam?
No,
Okay, I think if you do because I first also didn't really understand. If you look at the first exercise, it becomes really clear what they mean with it.
okay.
Maybe you can look at it after this, and I can still explain it if it's necessary. Okay. Where is my mouse? So, one more important Bayesian concept, the posterior predictive. I think you saw that multiple times during the course. When I did it, it wasn't there. So I have not much experience with it, but you predict new data points given a model trained on previous data. We saw that with the Game of Thrones regression. So we first train it on some data, then we sample weights, and then we get a new input, and we calculate a new y given those weights. You can use the likelihood estimate, but then you only get one weight or one value for each weight, and then you only have one value for y. But if you use the posterior predictive, you get samples from weights, and then you can have like a distribution around y, and it's more informative because you know the standard deviation and uncertainty around that prediction of y. Is that clear? Yes? Do you still remember from that exercise of game of regression? Not everybody completed that one. No? Okay. But do you understand this? Okay. Now I have an exercise for you. Do we need a break or after this exercise or something? Yeah, okay, but not yet. Or do you want a break? Okay. So we have this likelihood and this prior binomial beta, and I want you to write down the posterior distribution using the idea of proportionality, which I mentioned during the conjugacy slide. So you only need the posterior, not the marginal likelihood yet. Does everybody have paper? Ik ga 2 keer voor mijn budget af, wat ik altijd even. Maar dan moet ik wel echt heel veel flessen gaan drinken. Wacht, er nog eentje. Nee, slecht. Niet goed zacht. Voel het niet heel lekker, hè? Waarom niet? Eet je wel genoeg fruit, jongetje? Yes. Nee. Nee. Je hoeft echt maar 6 verdelingjes uit je hoofd te kennen. Dat is niet open boek, toch? Anders was die open boek. Ja, klopt. Ja, vorig jaar was het open boek en toen ik het deed al 2 jaar geleden. Toen ik die toets ging doen, toen ik mijn toets deed, had ik nog nooit een generator model gemaakt. Want nee, gewoon op die andere persoon aan mijn groepje. Does everybody know what to do? Or are you already finished? Should I give a hint? Yeah, I first have to think of a hint. So I think you all wrote down the distributions before, right? So you can fill them in and then see what form is and multiply them. And then you have some stuff that's to the same, like has the same base, and you can multiply stuff and then base gold. Je moet dus wel een goede bed aanpakken, hè? Omdat ik het zo verkeerd opstel. Yeah. Because you can just get the parameters. Ja, het was prima. Ik moet gewoon klagen. So did you calculate, multiply them? Did you multiply the prior and the likely? I just speak a little loud so everybody knows.
No.
Yeah, okay, but you wrote a dot between them, so that's what I meant. Okay, so yeah, so I think your x should be a p or your p should be an x. Yeah. Do you now see what you can multiply? Oh. Yeah, the p and the x in the likelihood and prior are the same. Or theta and yeah, it should be both be theta if you want to follow this, but it's fine to use p or x. That clear? Okay, and then you which yeah, what do you get then? What did you? Yeah. Huh? Okay. To write out the formulas and multiply them, and they can rearrange terms. That just stays there. Okay, yeah, I will just explain it later what you can do then. Okay, I will continue. I will show the answer step by step. So we have this is the likelihood. So x is k here. It's a bit confusing. And then this is the prior. So we can, if we would multiply these, we can see we can add this with this and this, or we can add the powers of theta and the powers of the 1 minus theta. This will stay in front. And then this is the posterior, yeah, the formula for the posterior. This is what? This proportional to this, only a normalizing constant, so the shape doesn't change. And the powers above theta won't change if you divide it by this. It will only influence this and this, which will result in this because we added the powers of theta, x plus alpha minus 1, and alpha 1 minus theta, which are n minus x plus beta minus 1. So we get that. And now you can see it has the form of a beta distribution again, and we can fill in the parameters. So if we look at the prior, if we use alpha as alpha, we get alpha minus 1. Here we have minus 1, so the new alpha is x plus alpha. similar for the new beta. So that just yes. Yeah, that's also only a normalizing constant. So if you say proportional, it has the same shape, but the scale can be different. This only because there's no theta in here, it doesn't influence how high everything will be. If they should be here, but then it won't fully match this. We will see that later. But this is like the most important part. That's like the signature of the beta distribution, right? Yes. Yes, indeed. So this is also proportional. Yes. Because that's just how beta distribution works. So if we have theta given alpha and beta, they're missing here, then we fill this in. So it's alpha minus 1. Here we have x plus alpha minus 1. The new alpha is x plus alpha. Okay. Then now that we know the posterior, we can calculate the marginal likelihood. I will just show this because why is the integral removed in the second step of the posterior? Because that's only a normalizing constant. The result of that integral will be one number. So it will only influence the height of the distribution, but not influence the shape. So we can say it's proportional to without the integral. Because the relative difference between 2 points will stay the same. Yes. So, okay, these images are really poor. Can you still read it? Okay. So now I changed the location of the let's go of the posterior and the marginal likelihood. So this is the marginal likelihood, the normalizing constant. This is now the posterior because normal Bayes rule is this is over here and this over there. But we can just multiply both sides with this one and then divide both sides with this one. And we now already know this one, so we can use it to calculate this. So to calculate the marginal likelihood with the parameters we found. So x plus alpha and n minus x plus beta. So those are the new alpha and beta of posterior distribution. We can also fill them in the normalizing constant. So we now we have this is the full posterior distribution. So first we only have everything this. So first we had this, but now because we know the parameters of the posterior distribution, we can also fill them in the normalizing constant, this part. And then you see it's similar to this one, but with x plus alpha and n minus x plus beta. So it's similar to this. If we then, just rearrange stuff, we can multiply this again. This is what we saw earlier as the posterior we found, or the proportional, but now with n over x and 1 minus 1 divided by the beta distribution, our beta function with alpha and beta. And then if we divide, you can see this and this, the back part. Can you also see it? Okay. Yeah. So this is just the theta and the 1 minus theta and its power. So this and this is the same. And we can divide both sides. So the result is this. So we only have this part, and this part. And then we can rearrange that even more to this. So this is the normalizing constant. As you see, there's no theta in it. So that's why we can leave it out when we want to find the proportional posterior, because it will only influence the height of the distribution. Do you see that? Yes. Yes. Yeah. So it's proportional to the likelihood times prior. The whole posterior is this part. This is the full posterior, but we can say it's also proportional to this. The shape is the same. The influence stays the same, but on a different level without this integral, but it's still similar. But if we then want to calculate this, we can multiply both sides with this. So then we would get this times this is this. And then we can divide both sides with this. So we would get this. So this is that divided by this, which we see here, but with different, yeah, it's written in a different way. Maybe. Can I draw on this? On that one. B times C divided by B. So posterior is likelihood times prior divided by marginal likelihood. We can say B times A is B times C. And then D is B divided by. Continuously. So is that clear? Nice. What? Okay. Yeah. Then I have two exercises about generative and graphical modeling, also with. Oh, is it clear for everybody in the chat? Okay, nice. You can always rewatch it or rewatch the stuff from last year because there's another example in that one. And just try it yourself with different conjugate distributions, maybe. Do you want a break right now? And then we will do this too, or do you want to continue? Yes. Okay, then we will continue, guys. Okay, do this exercise. So another farmer grows apples. This is from when I did the course, the practice exam. So I didn't write it. Over the course of 30 years, she noticed that the apples yield in YI, in year I for orchid, depends at least on one, the soil quality index that year, XS, I. Two, the amount of sprayed fertilizer that year, XFI. So we have multiple X's year I. And the number of injected pesticides that year, XPI. Constructive Bayesian model that the farmer can use to predict the apple yield for next year. If, yeah, and then XI plus 1, that's a factor, and are these three numbers. So the next X. You don't have to do much with this stuff, just construct a Bayesian network that can sample a Y from X. Yeah, how you should start? Okay, what is the output variable? One. Yeah. Yes. So what distribution can we use for, or what kind of variable is y? Is it between 0 and 1? Is it discrete? Is it continuous? Can it be negative? Yes. And not negative. So yeah. Okay, a bit weird. You still use a Gaussian, so it can be negative and not discrete. So you can assume you can use a Gaussian. So we can use a Gaussian to sample y. So what should be the input of the Gaussian? Which the variables? Yeah. What is standard deviation? What can we use? Yeah, just something we sample each one or another variable that has a prior. But you don't have to get any information from this for the standard deviation. Most of the times you don't. And what can we use as mean? Which variables are left in the text, which we can potentially use? Yes. So what kind of model is this? Yes. So how do we want to use all these x's for a mean? Yes. And how can we then construct such a mean? We have 3 x's, and the outcome is one number. So how can we combine those x's to one number? No. Yeah, or just add them. You can also take the mean indeed, but like we saw with the games of regression, so we multiplied each x with a weight and then added them. So is it now clear how you can approach this? Because that's almost everything. You still need a prior on your weights. Yes. Because often in regression models we have an input of the model. For example, with the coin flip, you don't have an input. You just have the sample and output from distribution. Here we have an input of 3 x's, and then we want to combine those to predict a y. So that's a regression model. Dat heb je allemaal niet nodig voor dit vak, hè? Echt? Zo simpel dit. Echt zo easy. Dat weet ik. Ik doe ook gewoon mijn best. Oké, dus. Okay, so y was the outcome variable. Yeah. We can sample it from a Gaussian. So write that down. Yeah. Yeah, yes, that's indeed a little bit weird, but that's what he did in the example. Maybe Poisson would be better than, and then with a rate, that's also variables, but yeah, that would be, that's not the only answer with a Gaussian, but I just want to follow his solution, Mach's solution, to not confuse you any further, which for some would maybe be better, yes. So we have a mean and a standard deviation, right? Just write a mu and a sigma. You can always later mu and sigma. No, that's a theta. Mu is the, yeah, but that's for MCMC. So that's the location of theta. Uit. Wat is met je handje? Hoe ziet die eruit? Ja. Does anyone need help, or you already finish it? I'll give you one more minute. So what can we use as mu? Yeah, so, and how can we combine them? Yes, yeah, with a multiply each x with weight. You can sample that weight again, or as well. From another Gaussian, yes. Or from something else, but a Gaussian makes most sense because then it can be negative. For regression, it makes sense that a weight can be negative because it can also have a negative correlation.
So you need to sample the mean with another.
No, the mean is deterministic because we have 3 x's and 3. I will just show the next one. I think everybody is done except for you. Yes. So this is a generative model and a graphical model. I will first explain the generative model. So we start from the bottom down because that's easiest to understand it. You sample a y from a Gaussian with a mean and a sigma. The sigma is, yeah, because in JAX you always use 1 over sigma squared, right? Or sampled as in the Gaussian, or you sampled something from the gamma and use that as the standard deviation. But the standard deviation in JAX is 1 over sigma, so we have to inverse the gamma if for normal. But if you just use a gamma, it's also fine. What? Mu. Yeah, okay. So we sample the standard deviation from here. It's not really important what you fill in. You can also just use an A and a B or something like that. You don't have to write or define the hyperparameters. And then we can define the mu as weight 0. So that's an intercept because we don't always want the regression to go through 0. And then we multiply each of the 3 x's with a weight. Yeah. And then we sample these weights from a Gaussian with 0 mean and 1 standard deviation. We want to sample them from a Gaussian because you want a way to that can be 0 or that can be negative because it can be a negative correlation between 2 variables. And you should not forget these. And then the graphical model speaks for itself from the generative model. So we have a y, it's an x, the betas, and the sigma, because mu is not mu is deterministic. It's not sampled, but it's just defined. You don't have to mention it in your graphical model, but you are allowed to. So the x, because this can also just be put in here, doesn't make a difference for your model, so you can leave out mu. But if it's easier for you, you can add it. Yeah, if you want to add mu, we would have a mu that's also in this box, so with I. And then that one will receive these 2.
Oh, right.
That will go to mu. Mu will go to y together with sigma.
Okay.
Yes. because sigma is not a hyperparameter because it's sampled, so it's not fixed. So it can change. These are the hyperparameters of sigma, but they're already defined. And if they're defined, you don't have to add them. But if we would put an A and a B here, or C and D, then you. Or if you would leave out this sampling and just have the sigma variable, you can write as a hyperparameter. I don't think it's necessary to have a squared here. It's because I think you didn't do that in previous exercise as well, right? You just write it down like that, but if you can add it, it's always better. Okay, is it clear for everybody in the chat as well? And here, does everybody have any questions? Okay, then I have another one. That's the last exercise. Should I read it or can you read it at the back? No, I know you can read it. Or I have my doubt. So a group of M is 10 people are interested in investing in cryptocurrencies, example given Bitcoin. You can see it's an old exercise. They can choose to invest in any of 20, and it's 20 different of these currencies. The probability that the person I invest in currency J depends on both the risk-taking nature of that person, I, number between 0 and 1, with 0 is no risk and 1 is extreme risk, but it can be between 0 and 1, so it's not a Bernoulli, as well as the perceived technical quality of the currency QJ, also a number between 0 and 1, with 0 is worst quality, 1 is best quality. We observe only Kij, which is 1 if I invested in J and 0 otherwise. We wish to learn both the risk-taking nature of all people in the group as well as the perceived quality of the currencies. Yeah, now what model can we use? That's your question. It's similar to the exercise we had in the second large assignment with the questions for students. Okay, dus begin onderaan. En onderaan, wat is de output? Nee, tussendoor, nee. Does everybody know how to approach this, or should I give some hints? Hints? Okay, so what is the outcome or to be predicted variable? It's often also an observed variable. So it's Kij. From what kind of distribution can we sample Kij? Or what kind of values does Kij can have? Oh, yes. Yes, Bernoulli. What is the input of a Bernoulli? Yeah, one probability. So how can we get that probability from this? I think you're one step too far. How can we make a probability from P and Q? P and Q are both probabilities, both between 0 and 1. No, not really. We have a probability that someone invests, and we have probability of or like we have a number that is the risk taking, so probability that someone takes the risk, invests, and we have probability that of the technical quality. But we want to combine those to one probability. Yes, you multiply them, because if you have one number between 0 and 1 and another, and you multiply them, it will always be between 0 and 1. So that's also again deterministic. So you don't sample anything, you just say that probability is Q, P times Q. And then how can we sample P and Q? Yes. And why do we want to use beta? Yeah, but there's also another reason. Yeah, it's not really necessary for the general model, but because the likelihood is Bernoulli, and because they're conjugate, we often want to use a conjugate. So if you use a Poisson, then the prior is often a gamma. If you use a beta or Bernoulli, the prior is often binomial or Bernoulli, the prior is often a beta, and if you use a Gaussian, the prior is often a Gaussian as well. Except for sigma, that's often sampled from a gamma. Yes. Yes, you can do that, but then you lose the conjugacy. So if you want to apply that model in real life, you can only do it once, and then you have a very difficult model, so you cannot incorporate more information. So that's more, it's not really necessary. I don't think you will get any point subtract, but just for your future work. Yes. Yeah, that's the same as uniform. It's a flat prior, you call it, so you don't have any information in your prior. Every probability is equal, so we can use beta 1, 1. Heel goed. Okay, can I continue? They show the answer? Yes. Okay. So this is the answer. So we already walked through it. So you sample Kij from Bernoulli, theta ij. Don't forget the ij here because we want a different theta for every combination of a person and a person. Yes, I want to mention that later. I will first explain this and then mention that. So don't forget ij and the theta, and then we can say theta is these two multiplied. We don't need the distribution like a wave because it's not a distribution. And also don't forget the ranges here. And then we can sample both from a beta. You can fill in 1, 1 or something else, but make sure it's not too strong because you fill in 101. It's a bit weird that you fill that in without any reason. Or you can use alpha or an A and a B, but you don't have to define anything from them. And then if we look at the graphical model, we have the E and the Q. Again, this is deterministic, so we don't have to include it, but you can include it, and then you would have theta. Which one you have the hyperparameters of P and Q, and the K should be, so this K should be between boxes as well. One box for I, one box for D. Because what he did, yeah, no, it's not wrong. It's just not very complete. He had one big box around everything with I and J, but this one doesn't use I. This one doesn't use J. So you want to have different boxes.
That way this is close.
Yeah, this should be in both boxes, but this should be in one. So you would have something like this and like this. So this is also incorrect because this one is not in a box for some reason. Yes. No. Yeah, that's a beta function. But you can use capital or not. It's neither to use capitals. Yes. You can still do it, but it's not necessary. Even if you have 1, 1 here, you can leave them in because they would represent these 1, 1. But you can also say 1, 1 and leave them out. Okay, is this one clear? This one was easier than the first one. Yeah, that was it for the crash course, but I can still answer some questions maybe about the practice exam if there's something difficult about that one. Is it difficult? Oh, okay. You're welcome. Geinig, hè? The modeling, or
Yeah, modeling.
No, it's not most important for the exam, but the most like for future. It's not for the exam. I think you just have to know some concepts, know how to do the math. Yeah, you will get probably, I don't know, but I think in most exams there's a question about it, right? Oh, you didn't look at it yet, but I think in most exams there is a question of model comparison, but it's not that every question is about model comparison. Maybe we should put it here.
That would be that's probably off.
Maybe we put one place.
Yes. Oh, that's also.
Okay.